Just want to say hello to everyone and welcome to the CDY seminar today. We are very happy to introduce Jacco Vink from the University of Amsterdam. And the title of today's talk is IXPE Studies of Supernova Remnants. And this is one of the series of talks that we have been focusing on IXPE results. We had one last week and 2 weeks ago, and then the next one as well will be focused on IXPE.
You are logged in.
Quick introduction, and if I could just ask people who are just joining, if you could mute, please. So Jacco is an associate professor at the University of Amsterdam. His expertise is in the field of high-energy astrophysics. He has broad interests. He started out working on supernova remnants and as cosmic accelerators. He also studies neutron stars, magnetars, pulsar wind nebulae, clusters of galaxies, and active galaxies. Jacco got his PhD from Utrecht University and studying the spectral morphology of supernova remnants. He then won the NASA Chandra Fellowship, which brought him to Columbia University, and this is where my paths first crossed with Jacco at that time. He's currently a faculty member at the University of Amsterdam. He's a member of CTAO, HES, CRISM, as well as IXPE. And very recently, just won the 2025 Humboldt Research Award. So that's really fantastic and congratulations. So let's welcome Jacco and get started. The format of the talk is 45 to 50 minutes, and then we will have some questions, and then followed by general discussions. And we are recording this, and please mute yourself. And just drop your email in our chat if you want to get added to our mailing list. So thank you, Jacco, for giving us the seminar, and I hope you continue to join these. It's every 2 weeks and at the same time, 9 a.m. US. Thank you.
I will try. Yeah. So thank you very much for having me, and indeed it's a pleasure having you as a host. As you recalled, we shared an institute in 2003. Let me see how my slides are going up. It takes some time apparently. So there it comes.
Yes, it looks
Okay,
good.
I slightly changed the title. I wasn't aware actually of the title I've given. But of course, you know, what we want to do with X-ray polarization is probe the turbulence of the magnetic field and the geometry of the magnetic field in young supernova remnants. I will say a little bit more about the background for why this is interesting, and also about X-ray, non-thermal X-ray emission from supernova remnants. First of all, I would like to thank all my collaborators in IXPE. It's a very big team, but especially those people listed here who are part of the Supernova Remnant Working Group, which is led by Patrick Slane. Every Friday we are still meeting. And some of the names that you see here are people who have led one of the IXPE papers on supernova remnants or are very high up in the list. So first, a little bit of background. Well, you had already probably quite some lectures on cosmic rays and IXPE. I would like to go back all the way to 1911, when Victor Hess discovered actually what he called penetrating rays, which only were in the 30s recognized as charged particles. And of course, that led to the quest for what is the origin of cosmic rays. I guess when we deal with IXPE, we know that there are cosmic rays, electronic cosmic rays, but we still want to know how are they being accelerated. Now, the first notion that supernova remnants are very important for cosmic rays comes from Bade and Zwicky, who suggested that supernovae are basically the transition of a massive star into a neutron star, and in more or less the same paper said, well, probably they are the sources of cosmic rays. Although at that time it was thought that the cosmic rays really come from the supernova event itself, not from the supernova remnants. And then Joseph Shklovsky in the 1950s suggested that the radio emission that was discovered of some sources was from supernova remnants, and that this is caused by relativistic electrons, so-called singleton radiation. And the prediction of that would be that it would be polarized, which was soon found out to be indeed the case. So here we have the cosmic ray spectrum. It's more or less a power law over many orders of magnitude, from 10 to the 9 to 10 to the 20. However, if you multiply it, you see that there's some substructure there. And the idea is that where we have this important Needis break here, that these are galactic cosmic rays. So cosmic rays accelerated in the galaxy. Maybe it's even up to 10 to the 17, 10 to the 18 electron volt. There's still a quest to understand what's really happening here. For supernova remnants, we think we can go up to 100 TeV. So most of this will be probably from supernova remnants, but we don't fully understand everything here yet. Now, the idea that supernovae or supernova remnants are responsible is mainly energetically. If you look at the steep power law, of course, most of the energy in cosmic rays is at low energies, 10 to the 9, 10 to the 10. And we know from radioactive nuclei in the cosmic rays that the escape time is around 15 million years. So that's how long they stay in the galaxy. And in order to fill the galaxy with all those cosmic rays, where we have a local probe, from the cosmic rays that reach the Earth, we know that the energy constraint is that we need 6 times 10 to the 40 ergs per second. So the supernova power should be the energy needs there. The supernova power itself is 6 times 10 to the 41, for which we take about 2 supernovae per century and an energy of 10 to the 51 per supernova explosion. And if you see about 10% of that energy should be converted to cosmic rays in order to explain the energetics of cosmic rays in our own galaxy. Now, with IXPE, of course, we are targeting mostly the electrons. The electrons are energetically not that important. It's much less than 1% of the cosmic rays energetics. But of course, they radiate much more efficiently, so they are the best probe of cosmic ray acceleration in supernova remnants and other sources. Now, a little bit about supernova remnants. Of course, these are the sort of debris of supernovae, but it's actually much more. It's created by the shock wave generated by the explosion. The shock wave sweeps up a shell of hot material, but at the same time, there will be also a reverse shock going back into the ejecta. So the outer ejecta are a sort of a piston, and the hot piston at some point will drive a shock wave going back, and which we call the reverse shock. Now, the evolution you see here, this is for the forward shock. This is a particular model. The reverse shock, despite its name, initially goes outward, but at some point turns around and goes inward. And only at late stages, the reverse shock will have reached the center, and the whole thing is very hot. The only thing is that the outside is rather dense, so that's what we see, and the inside will be hot, but very tenuous, so very difficult to see. In general, although there are many exceptions here. So mostly we think about cosmic ray acceleration at the forward shock, but I will show one case where actually the reverse shock also seems to be very efficient in accelerating particles. So as I said, Barton and Zwicky really saw that the supernova was accelerating cosmic rays. And after radio emission from supernova remnants was discovered, slowly you see that the paradigm shifts from cosmic ray acceleration by the supernova to cosmic ray acceleration by supernova remnants in the shocks. And that process was completed when, in 1978, the theory of diffusive shock acceleration was established. Now, if we think about the radio singleton emission, we're talking basically about GeV electrons emitting because they move in this magnetic field. And almost all supernova remnants are discovered using this radio emission. And so this really provided the paradigm shift to say it's actually the shocks that are accelerating, the shocks of the supernova remnants that are accelerating particles, and we can probe that at least in the radio with radio singleton emission. Now, only since 1995, we know that we can even get X-ray singleton emission from very young supernova remnants, but in that case, we're not talking about GeV electrons, but say 10 to 100 TeV electrons. And we only see it in very young supernova remnants. So here we have 3 examples. It's in all these pictures, sort of blue is what is X-ray singleton radiation. So here you see supernova 2006. It's rather big. It's around the size of the moon. And this bluish glow that you see here is X-ray singleton emission. The red here is supernova debris. This is a type 1a, and this happens to be mostly oxygen in this particular case. So what this immediately establishes, of course, that the particle acceleration should happen really at the shock front. If it was imposed by the supernova, of course, the whole thing should glow in X-ray singleton radiation. But it's really at the shock front where we see the singleton emission. The same so for Tycho supernova remnant 1572. And here you see in blue purplish also X-ray singleton emission. And it's a very thin, narrow rim here. The green stuff here is silicon emission, freshly made silicon. And the red stuff here is in X-ray what you see from iron. Again, this is a type 1a supernova remnant, but we are really interested in this very thin rim that you see here. And the same goes for Cas A, which is a core collapse supernova remnant. Again, we see in green silicon, in red we see iron, but also magnesium, and in blue we see an X-ray singleton emission. And like in Tycho, we see that X-ray singleton emission is really from the regions where the shock is, and it's very, very thin. Cas A is also important or special in the sense that you see also quite some non-thermal emission from this region, especially in the west, but also a little bit towards the center. I will come back to that later. So why study polarization in astrophysics? Well, in general, of course, polarization shows that there is some geometric dependence. Most polarization is induced by some scattering geometry. But in the case of singleton radiation, of course, we are talking about the magnetic fields imposing a preferred direction. So singleton radiation is caused by relativistic electrons or positrons spiraling around the magnetic field. I know Felix also talked about at some point a proton singleton radiation, but that's much less efficient. So whenever we see it in galactic sources, it's invariably electron positron singleton radiation. And here you see a picture from actually Wikipedia. So you have a magnetic field here. The electron spirals around it, and then the polarization direction is perpendicular to this magnetic field. The radiation and the frequency is determined by the fact that you have some Lorentz boost of your emission. So normally, if it's not relativistic, you would emit in all kinds of directions, but you get a very narrow cone. And whenever your eye sort of meets the cone, you have a brief flash which determines the frequency of the radiation. Now, it's intrinsically polarized. It's not completely polarized. And actually, if you have a power law shape for distribution for your electrons, your polarization fraction depends on the power law slope alpha, which is the radio power law slope. And for radio emission, where alpha is typically 0.5, 0.6, the maximum polarization that you can get out of singleton radiation is 70%. Now, I already talked about that we think that diffusive shock acceleration is accelerating those particles, and that's true for protons, but also the electrons. In diffusive shock acceleration, the particle gains energy by crossing repeatedly the shock front and sampling both frames, the unshocked frame and the shocked frame. The unshocked frame we call upstream, the shocked frame we call downstream, and there is a velocity difference there. And the particles feel this velocity difference because there are plasma waves, and the particles are scattering on those plasma waves, and that's how they sort of know what is the local velocity field. Per crossing, you gain energy in diffusive shock acceleration, that is delta E over E, is of the order of delta V over C, and C being the particle velocity, but of course for relativistic particles, this is the speed of light. Now, if you have this is diffusive, so the particle diffuses here, and then there is a finite probability to cross the shock front. What is very important here is the diffusion coefficient, which is 1/3 times the particle speed times the mean free path. What we usually take for the mean free path for scattering on those magnetic fields is the gyro radius of the particle. And then we have this eta factor. So the gyro radius is the minimum mean free path of the particles. And we usually parameterize that with this factor eta. Now, the acceleration time that you can get out of that is 8 times this diffusion coefficient divided by the shock velocity squared. And the maximum energy that you can get out of that without any energy losses is inversely proportional to this factor eta. which is the diffusion length scale in terms of the, not the length scale, the diffusion scattering length scale as a function of the gyroradius. So it's an energy dependent factor times the sort of mean magnetic field that you have there times the shock velocity squared times the time available for accelerating particles. There is a relation between this gyro factor eta and the magnetic field turbulence, namely eta is inversely proportional to delta B over B squared, the inverse of that. And so the best that you can get is an eta around 1. So that is actually the shortest diffusion scale that you can get. In practice, you expect actually much larger, but we know now that in young supernova remnants, it may be close to 1. This already points out that you need turbulent magnetic fields to accelerate. So this doesn't bode very well for measuring polarization, right? Because the maximum polarization is for a very straight magnetic field. If you have a very turbulent magnetic field, it will reduce your polarization degree. This is sort of the cartoon picture that we have of this. So you have particles bouncing back and forth between both sides of the shock front. They're scattering by the MHD waves, and that's how they gain energy. Delta E over E is delta V over C. Now, if you go to X-ray singleton radiation, I already told you that you need 10 to 100 TeV particles. The energy that you get for your typical photon energy depends on the magnetic field, and it depends on the energy of the particle squared, according to this fashion. Those electrons cool very fast. So in the radio, the GeV electrons, they take 100,000 to 1,000,000 years to really cool. However, the X-rays, or the 100 TeV particles, they take about 10 to maybe 100 years to cool, depending on the magnetic field strength and the energy of the particle. So that already tells you, perhaps, why we have such very thin filaments in X-ray and very close to the shock front. Only if you are very close to the shock front, the electrons still have the energy that they gained through the acceleration process. Once they are moving away, they lose energy, and at some point you don't see them in X-rays anymore. So this immediately tells you that if you see X-ray singleton emission, we have particles that have been accelerated over the last 10, 20 years. And it also is additional evidence that it's really the shock acceleration that is providing the energy for these particles. Now, if you look at what type of energy can you get out, I already showed you the acceleration time. If you set the acceleration time to the cooling time of the particles, and then you say, okay, for the equilibrium energy that I get, what is my photon energy? What you get is that your photon energy is around 1.4 keV for independent actually of your magnetic field. This is actually something that Felix first reported. So it is inversely proportional to this factor eta, and it is proportional to the shock velocity squared. This immediately tells you that you only expect X-ray singleton radiation if the shock velocities are very high, right? If this falls below, say, 3,000 or 2,000 kilometers a second, the cutoff energy, where the spectrum should slope over, is below 1 keV, and you don't expect X-ray singleton radiation anymore. The other thing that it immediately tells you is that in order to get X-ray singleton radiation, the turbulence factor, this eta, this gyroradius factor, must be very small. 1 is the smallest, but then you get for sure X-ray singleton emission. But if you have, say, an eta of 10 or 100, you don't expect any X-ray singleton emission. So this also tells you that if you look at this picture here and you see X-ray singleton emission, the turbulence level must be very high, and you're close to this minimum of eta is 1, which is called the Bohm limit. So this is something that happened over the last 25 years or so, that we have recognized that in young supernova remnants, we have fast shocks, we have acceleration there, and the turbulence factor near the shock must be pretty high, close to 1. You can also use the theory about the cooling and the advection away from the shock to say, okay, if the magnetic field is very high, the particles don't go very far from the shock with this 100 TeV or 10 TeV energy. So you can convert the size of this width into a magnetic field strength. And it turns out that you get, if you measure it, a 10 to the 17 length scale corresponds to 110 microgauss. So measuring the width of these filaments, and I showed you 1006 where it's a little bit wider, gives you immediately a measurement of the magnetic field strength in those supernova remnants. To wit, this is the downstream magnetic field, so after the shock passage. And you can see, the magnetic fields turn out to be very high. So this is from a review of more than 10 years old. So here you see the shock width. Here you see the diffusion length scale or the advection length scale that we can get out of that. And here you see the magnetic field. So you see that for all those young remnants, we get magnetic fields that are 30 microgauss or even much more. For Cas A, maybe even 250 microgauss, which is much more than you would expect from, say, the interstellar medium or circumstellar medium of young supernova remnants. So this was evidence that magnetic fields are actually not only very turbulent near young shocks, but are probably amplified. And one of the mechanisms for the amplification is the so-called Bell instability, in which the stream of cosmic rays induces a current in the upstream plasma. And because the particles are interacting with this magnetic field generated, you get additional turbulence, which gives you a magnetic field amplification. And Bell predicted that the B squared should scale with rho v s to the third. So the density times the velocity of the shock velocity cubed. And indeed, in this plot, what you see is if you have the shock velocity on the one side and B squared over the density on the other side, there seems to be indeed some linear relation. It's very difficult to get the exact slope. And the reason is, of course, we don't really have a lot of dynamic range in velocity. And actually, the last point here is not a young supernova remnant, but supernova 93J, where the magnetic field has been measured in a different way. But it seems to be along this line. So there at least is tentative evidence that indeed this relation holds. So the higher the density and the higher the shock velocity, the larger the magnetic field amplification. I said to you that we have also a reverse shock. Usually it's not implied in particle acceleration, but it may actually be very important. And the most important case in that sense is Cas A. Here you see two plots from a paper by Eveline Helder, my PhD student at the time. Here you see the spectral index. Everything that is blue is probably thermally dominated, and everything that is yellow is probably non-thermally dominated, so X-ray singleton. And you see sort of two regimes of particle acceleration. One is at the outside, so that's the forward shock, but also at the inside. And it seems to be peaking really in the western region. So something special is happening in the west. The whole reverse shock, if this is tracing the reverse shock, is a little bit shifted, which we can also see in the radio, where we see free absorption from unshocked ejecta. So basically this traces here where we expect to see the reverse shock. Now, what is very important, if in Cas A we have non-thermal emission in the reverse shock, first of all, the reverse shock must have a very high velocity. And secondly, the filaments there are also quite thin. That means that there must have been magnetic field amplification there as well, whereas in the reverse shock, we don't expect a very big seed magnetic field. So the amplification must be from a very low magnetic field to magnetic fields of the order of 200 microgauss there. And indeed, if we do an X-ray expansion measurement, and I did something 2 years ago, here you see the forward shock velocity that we measure. It's around 5,000 to 7,000 kilometers a second in Cas A. Here we see the reverse shock velocity, and it's going actually in reverse in the western region. So basically, the forward shock is going outward in most of the remnant, but in the western region, it's going inward. And what you then have is a very high shock velocity, because it's the shock velocity is really determined by the velocity of the shock going inward and the ejecta going outward. And this relative velocity is shown here in this dashed line. And you see that the reverse shock velocity in the west is really going up to even 8,000, 9,000 kilometers a second. So that's the most powerful shock that we have in Cas A. Now, a little bit back to the magnetic field geometry. Of course, if you have a shock, and usually you have a magnetic field that is sort of oblique to the shock normal, a shock compresses only the parallel magnetic field, which means that you get a tangential magnetic field out. So if you have a perfectly parallel magnetic field, it stays parallel, but if you have a slight shock angle, it becomes a tangential magnetic field. So naively, what you expect for your singleton radiation, if there's not too much turbulence, is that your magnetic fields are tangential. So basically, they align with the shock. Of course, DSA interferes with that. For DSA, what you need is magnetic field turbulence. It's self-generated by the cosmic rays. And the self-generation of the turbulence is actually distinguished between resonant. That means that the wavelength is sort of the same as the gyro radius. So if you have cosmic rays with a particular energy that generates a lot of turbulence with the same gyro radius as the wavelengths of this magnetic field waves. And then you have the non-resonant one, the Bell instability that I already talked about. Now, most of the theories actually go about the upstream medium. So we don't really know what happens to the turbulence downstream of the shock. It certainly is there. It's supposed to also die out at a certain range, but we don't know that much about the downstream turbulence. Now, if we look at what the radio emission tells us, already in the 1970s, it was clear if you look at supernova remnants, you get a radially oriented magnetic field in young supernova remnants. So like here, Cas A, here we have the magnetic field vectors, and you see it's like the spokes of a wheel. If you go to mature supernova remnants or older supernova remnants, we almost always see a tangentially oriented magnetic field. So the tangentially oriented magnetic fields is what you basically expect if you compress the magnetic field in the shock. And then it's not quite clear how you get a radially oriented magnetic field in the young supernova remnants. It's not, that something that you naively expect. Here you see a very beautiful image from 1987A of Cas A, where the color indicates the polarization angle, and you see a sort of a clockwise rotation, which is clear for a radially oriented magnetic field. Now, the early theories actually for why we have a radially oriented magnetic field focused on radially Taylor instabilities in the contact discontinuity. The contact discontinuity is that part of the shell where the shocked ejecta meets the shocked interstellar medium. That's radially Taylor unstable, so you get all those radially Taylor fingers, and they stretch the magnetic field. More recently, in 2013, people also thought about Richtmeier-Meskov instabilities, which could happen at the shock front. So if you have just a little bit of a clumpy medium, you stretch your magnetic field, so you stretch your plasma modes behind the shock front, and it tends to stretch the magnetic fields in the radial orientation. And then there was another theory by West et al. That said, well, maybe we have a sort of an observational bias. We only see singleton radiation from those parts where we have a parallel magnetic field. There is some evidence that if you have a parallel magnetic field, so basically a radially oriented magnetic field, you have better particle acceleration. And then if you have only in those pockets where you have a radially oriented magnetic field, if only there you have particle acceleration, then it looks like it's radially oriented, but it's just an observational bias. You don't see emission from the in-between region, so to speak. So this is sort of the scene that we had before IXPE arrived. But so why are we also interested in X-ray polarization, whereas we already have radio polarization? Well, first of all, radio polarization tends to be focusing or seeing the whole supernova remnant, and mostly the bright parts where you go through the shell. So in the shell you have many different cells, so that tend to depolarize because maybe the orientation is everywhere a little bit different. Also, if you go in the shell, that's part close to the contact discontinuity where this Rayleigh-Taylor fingers may play a role in reorienting the magnetic fields. If you go to X-rays, we are really focusing on this very thin region very close to the shock front. So we have a much more direct probe of what is happening at the shock front instead of further downstream of the shock. The downside, of course, is that we can only probe this for relatively young remnants where the shock velocity is still 3,000 kilometers a second or more. And another observational problem that we have is in some of those remnants, a lot of the X-ray emission is actually thermal X-ray emission rather than non-thermal. So we always then need to separate the thermal and the non-thermal emission. There are some exceptions. RSJ 7013 and Vila Junior, which you see here, only have non-thermal emission above 2 keV. Actually, you see here other emission as well, but it is from the Vila supernova, which is very soft. And in 1006, actually also at the rims, there's very little thermal emission. But for CAS-A and for 1572, we really also have to take into account the fact that there is some thermal emission. And whenever we measure polarization, we have to correct for the fact that there is some contamination from thermal X-rays. So now to IXPE, you had already some talks about it, so probably you know more or less what it is. It was launched in 2021. It's a collaboration between the US and Italy. The US provided the spacecraft and the mirrors, and Italy provided the detectors. Here you see a schematic view of the telescope. It had this extended boom that had to unfold. That caused some problems in the beginning because actually it was not that stable, and also the alignment was not ideal. It has 3 X-ray telescopes and 3 detectors. And the detectors are the Italian gas pixel detectors, which you see here. It uses the photoelectric effect. So an electromagnetic wave comes in, and then it ejects a photoelectron, and the photoelectron has a tendency to be ejected along the electromagnetic field vector, the electric vector of the field. It's not perfect, so the angle is distributed as the cosine squared of the electric field vector. So the angle phi shouldn't be taken as being the polarization vector. It's actually has a tendency to be aligned with the magnetic field, with the electric field vector. And then it turns out to be quite difficult to get from that the ejection, because what happens is you get this photoelectron, it makes a cloud of secondary electrons. And from the shape of those secondary electrons, which are recorded, you have to see where the impact point is. In this case, it's here, and what the photoelectron vector initially was. So where you see most of the emission is actually where the electron cloud ends up, but this is the initial one. So you see, it's easy to make a mistake there, and that adds to the error of your measurements. So what we basically have, we have a photon list, and for every photon that is measured, we have this direction phi, and we can create Q and U maps out of that by just summing the cosine of 2 times this phi with a factor 2. And the factor 2 is here because it's cosine squared distributed, and that this corrects for the fact that you that it's not really the electric vector that you measure, but the photoelectron direction that you measure. Since phi has some finite error, and that can be quite large, and actually the error becomes larger if you go to lower energies, the polarization effect that you measure is less than the actual polarization factor, and we use the modulation factor as a measure for that. So this tells you what the Q and the U are for a 100% polarized source. So if you have 100% polarization at 8 keV, you measure a Q or a U that is around 0.6. And you see it's rapidly going down below 3 keV. For that reason, we often just measure polarization above 3 keV. Certainly, if there's also thermal emission, in some cases we can go all the way down to 2 keV. Now, what were the naive expectations for what we wanted to measure? Well, from the radio observations for young supernova remnants, we expect a radial magnetic field, but we don't quite know where this is generated. And really at the shock front, you still expect a perpendicular magnetic field until whatever mechanism operates to stretch out the magnetic fields. We also expect quite some turbulence because for DSA we need turbulence, and we know that we have a lot of turbulence, otherwise we wouldn't see any X-ray singleton emission. But on the other hand, we have a magnetic field compressed, so that may prefer a tangential magnetic field. We have a steep X-ray singleton spectrum. So intrinsically in X-rays, we expect a higher polarization than in the radio. So if we would have a big pocket full of a certain magnetic field geometry, we expect a quite high polarization. We have very small filaments very close to the shock front, so the line of sight effects are much less than in the radio where you look through the whole shell. A problem that we have in interpreting is, of course, that the predictions are mostly for a turbulent field upstream, say the Bell instability, whereas, of course, what we are always measuring is the downstream magnetic field properties. So this is some simulation done 5 years ago. It was targeted at Tycho supernova remnant. It is by Andrei Bykov. And what you see is that the predictions are basically all over the place depending on what you put in. So it could be as low as 5.6%, maybe even up to 74%, depending on the compression ratio. The higher the compression ratio, the more induced tangential magnetic field is, and the higher your polarization fraction. If you have quite some turbulence, you expect a low magnetic field, but it of course also depends on what are the length scales of the turbulent field modes. And in this particular simulation, it was 10 to the 18 centimeter, which corresponds to roughly the resolution of IXPE, which is 25 arc seconds. Now, so for the analysis, what we use is this Q and U, which is the summation of all the individual Q and U's from the event list. The expectation value for Q and U without polarization is, of course, 0. And that means that if you do a Q squared per pixel divided by the variance of Q plus U squared by the variance of U, you have 2 Gaussian distributions. If you add 2 Gaussian distributions, you get a chi-square distribution with 2 degrees of freedom. So we use a chi-square analysis to say, okay, yes, here we clearly have polarization, and here we don't find any evidence for polarization. Here on the right, you see the first image that we took with for Cas A with IXPE. In the contour lines, you see what Chandra provides, and the pixelated one shows IXPE. And you see a sort of bluish glow here and at the outskirts, and that's the X-ray singleton emission, whereas the more pinkish, reddish color indicate the thermal emission. Another way is actually using a spectral technique where basically per energy bin you create a Q and a U, and you can fit that simultaneously and fold it into your model. And the nice way of doing that is that you can more naturally account for the fact that you also have some thermal emission. So the first observation was Cas A, which was quite exciting, but also a little bit scary because it was only 2 months or less than a month after the launch. There were still many calibration issues that we had to deal with. For instance, the images were not aligned. We had to do that manually. There were some other errors in there. The PI energy reconstruction was not very perfect, so we didn't do any spectral analysis. We totally relied on imaging as a whole. The effective exposure time was around 800 kiloseconds. So this is what we get. So here you see a chi-square map. So this indicates if the chi-square is high, there is some indication of polarization. And we got 3 sigma detections in those 2 pixels here. But a 3 sigma is not really enough because you have many pixels. So that is a number of trials. So if you take the number of trials into account, it was not a 3 sigma detection. So we didn't call it a detection yet. If you trust it as a detection, the polarization degree in those 2 pixels is around 15% or so. So we didn't have a firm detection, but we write on another method then, and that is we, per pixel, we said, what if we have a radial or a tangential magnetic field? We use the symmetry of the problem, and we have a Stokes Q and U that we locally define, and it rotates around the supernova remnant. And then you can add all the Q's and U's over the region of interest, and then indeed we got secure detections of 4 to 5 sigma. The polarization degree turned out to be very, very low, so around 2 to 3.5%. If you correct for thermal contamination, it's still on the level of less than 5% polarization. So it looks like it's a very turbulent magnetic field there. And to our big surprise, we had hoped for a tangential direction so that, the hydrodynamic instabilities kick in further downstream outside the X-ray singleton rims. But what we found is that already in this very thin filaments, there is a radial magnetic field. So within 10 to the 17 centimeter of the shock front, the magnetic field is already radially stretched. Then we went to Tycho, and you may know from Tycho that apart from this very thin filaments at the shock front, there are also these Tycho stripes. So they look like a sort of a regular pattern, maybe induced by cosmic rays there. And you can sort of imagine that this must have a high polarization degree, that this sort of tells you the stretching of the magnetic field lines there. So we expected to see this back in our polarization maps. But this is actually what we found. The Tycho stripes are more like here. And here we use a smoothing technique to see where we have the highest polarization, and it turns out to be slightly above that, where we indeed have some very bright X-ray singleton filaments. So we didn't find a very high polarization degree there. So what we find here, so these are the regions that we investigated. We took the whole rim using this technique of using the spherical symmetry. We looked at the bright spot that we found in the smoothing map, and we looked at the Tycho stripes. And the Tycho stripes is only a 3.7 sigma detection and a polarization degree of only 7.3%. For the whole rim, so for the whole thing, we found a 9% polarization degree. And in this region F here, we found a 10% polarization degree. So the stripes don't really stand out in the polarization map, which is maybe surprising. Then 1006. We have now a second pointing here, which is in the works, so expect that within 1 or 2 months or so. But for the PV phase data, we concentrated on the northeastern part, which is the brightest anyway. This is the Stokes I map, so the normal count map, and this is the polarized signal that we detected. And you see actually that the polarization degree goes a little bit more up there. From the width of the filaments, we know that the magnetic field must be around 80 microgauss, although inverse Compton emission gives you more like 30 microgauss. And this is where we find semi-significant detection, and this is the most significant points. This is the polarization degree, and what you see is you go up to 25% and typically more like 20%. So that's much more than CDHY and much more than Tycho. We tend to use these types of diagrams to show you what is the crosstalk between a polarization degree and polarization angle, because these are not independent quantities. Q and U are independent quantities. Polarization degree and polarization angle are not. Again here, and also in Tycho, I forgot to tell that, but again here we have a radially oriented magnetic field. So whatever is happening to CDHY to stretch the magnetic field is probably also happening in 1006, which is surprising because CDHY has a very clumpy medium, and 1006 should go in a much more smooth medium because it's very high up the galactic plane. And then came the big surprise. We also looked at RJ 1713. This supernova remnant is completely X-ray singleton dominated, no thermal emission there. We didn't know what to expect because there are no good radio maps that have measured polarization. So the IXPE polarization measurement is the first polarization measurement for this supernova remnant. We looked at this bright spot in the northwest, and this is the Stokes eye measurement, and these are the extraction regions that we used. In this case, depending on your favorite point of view, the magnetic field is more likely 10 to 30 microgauss. It's faint in the radio. And here you see the polarization measurements themselves. And the vectors that we show here are the magnetic field vectors. And so the big surprise here was we were just getting used to all those radial magnetic fields, and then suddenly in RSJ-7013 we found out that the magnetic field is tangential here. So this is consistent with a crossed magnetic field crossed by the shock. The highest polarization fraction is very close to the shock front. So it could be that if you go further downstream, you have some stretching, and that sort of depolarizes the signal. It's a very solid detection, as you can see here, right? If the outer contour doesn't reach the zero, we have a very good detection. So this is, I think, a 5 sigma detection. And then finally, the latest paper, which appeared, I think, December 2024, Villa Junior. Again, we looked at the brightest part here. Unfortunately, here we show the electric vector, not the magnetic field vector. These are the significant points that we find, and we see that the magnetic field here, so the electric field is tangential, which means that the magnetic field here is tangential again, like in RSJ-1730. The magnetic field estimate for this remnant is sort of 10 microgauss. It's probably the oldest supernova remnant in the whole bunch. So it's on the border of being called mature supernova remnants, I would say. On the other hand, it must be dynamically young because you need shock velocities of 3,000 kilometers a second. The polarization degree is 16 plus or minus 5%. One technique that we tried often, not always published, but behind the scenes, is using smoothing techniques to see where we have polarization. And here I show the smoothing maps. And it's actually a very good method to see where the highest polarization degrees are. So here you see everything above 2 sigma has now radial magnetic field vectors here. And indeed you see consistently here it's tangential in all those points. Even if we do individual pixels, it's tangential or it's radial in the Tycho, in 1006 is radial, but here we see tangential magnetic fields for RSJ-7013 and Villa Junior. So this is an overview of all observations. It looks like the youngest ones and the ones with the highest magnetic field, say above 30 microgauss, have radially oriented magnetic fields. If you go to the ones that have a lower magnetic field, it turns out to be tangential. And these are also the oldest ones that we have. Yes, let's go to the turbulence and the geometry now. First of all, we had the expectations imposed, say, by Andrei Bykov's paper, where we could have quite high polarization degrees, up to 74%. However, what you have to know is, of course, that the IXPE resolution is pretty weak. It's more of the order of 10 to the 18 centimeter for most supernova remnants. But the turbulence mode that we expect, say, from Bell's turbulence or resonant instabilities are more like 10 to the 16 to 10 to the 17 centimeter, and 10 to the 15 for the resonant ones. So the turbulence where we expect to see the most turbulence is below the resolution of IXPE. So if you would have very high resolution, maybe we would see pockets of high polarization, but everything is smeared out because of the IXPE resolution. The Bykov simulation had a cutoff spectrum around 10 to the 18 centimeters. So there you would sort of resolve the peaks in the turbulent spectrum. So that tells you that most of the turbulence must indeed be below the resolution of IXPE. So what we expected is at a shock front a tangential magnetic field and maybe some stretching later. What we found now out is that the stretching of the magnetic fields must happen very close to the shock front, within 10 to the 17 centimeter for Cas A and Tycho's supernova remnant. So this suggests that it's not the contact discontinuity where we have Rayleigh-Taylor instabilities, but probably something at the shock front, which would be the Richtmeier-Meskov instability explored in this paper by Inoue in 2013. But you need a very clumpy medium. So the question is where the clumping actually comes from. Andrei Bykov in a later paper said, well, maybe the clumping is actually associated with Bell instability, because apart from inducing some magnetic field amplification, it also induces density fluctuations, and the density fluctuations cause maybe the triggering of this Richtmeier-Meskov instability. Now the competing model by West et al., where you have pockets of parallel magnetic fields, and there you see the acceleration doesn't seem to be very appropriate for X-rays. And the reason is, of course, that the diffusion length scale of these particles is quite wide. So whenever you have this pocket, you know, the electrons would diffuse out of these pockets and you would probe much more regular magnetic fields. So this mechanism can be valid maybe for radio, but it's certainly not valid for X-ray synchrotron, because the direction, the local direction would be washed out by the diffusion length scale of the 10 to 100 TeV electrons. Now, a suggestion that I think might be valid myself and is related to this Bell instability. I already told you that what we basically see is that B squared downstream of the shock seems to be a proportion, a constant times rho v s squared, or maybe rho v to the third. But for very low densities, what you expect is actually that the instability that you get is sort of comparable to the average magnetic field that was already there. So Bell induces some turbulence, but it's a very minor compared to the stable magnetic field that was already there. So where do we expect this turnover point? Now what we can say is that if we normalize everything to Cas A, where the density at a forward shock is around 2 per cube centimeter, the shock velocity is around 6,000 kilometers a second, then we can see what this K is. It's around 0.15%. If you now say, what do we get when is B0, when is the Bell-induced mode 20 microgauss comparable to what you expect for the compressed magnetic field of, say, the interstellar medium? The answer is that you need a density of around 0.05. And that is very comparable to the densities that we expect around RxA 7013 and Villa Junior. The reason that these still have a very high shock velocity is that they have been expanding in a very low density environment, probably created by the winds of the progenitor material. On the other hand, there is a paradox here, because on the one hand, you don't want to have a lot of turbulence there, but there needs to be at least some turbulence, otherwise we wouldn't get X-ray synchrotron radiation. Remember that eta needs to be close to 1 in order to get X-ray synchrotron radiation. So there is a little bit of a discrepancy here, I would say. So the possibility that I'm advocating here is that, yes, you get very turbulent magnetic fields because of the Bell instability, but at low densities, the Bell instability is only a minor addition to the magnetic field that's already there, and therefore we see in those remnants a tangential magnetic field because the turbulence is much less, and the turbulence generates basically this magnetic field stretching. And so here is my summary. So with IXPE, we have a new window on studying supernova remnants and the magnetic field geometry, which is very important, of course, for assessing the cosmic ray acceleration properties. We targeted young supernova remnants because only these have X-ray synchrotron radiation, where we expect polarization from. The X-ray synchrotron radiation only is there if you have shock velocity of more than 3,000 kilometers a second and a very turbulent upstream medium. And in those remnants, we already have evidence for magnetic field amplification. And the IXPE results are that we generally find a very low polarization fraction, 5 to 30%. For Cas A, the lowest, around 5%, which requires also quite some downstream turbulence. I didn't go much into that, but we don't know that much about what level of turbulence is there downstream, but now we have an observational measurement there. In young remnants, we mostly find radial magnetic field, except in RJ 1713 and Villa Junior, which are the oldest of the two. So X-ray singleton is not equal to being a radial magnetic field. What we don't understand is, why do we sometimes see a radial magnetic field and why sometimes a tangential magnetic field, and what induces this? Although the Richtmeier-Meskov instability seems the best case for why we see radial stretching of the magnetic field in some supernova remnants. RCA 1713 and Villa Junior are the oldest, but probably also the lowest magnetic fields that we see here. And this may be the reason that here we find prevalently tangential magnetic fields. But of course, we still need some turbulence there, otherwise we wouldn't see any X-ray singleton emission. So with that, I would like to conclude. Thank you.
Thank you, Jacco. That's really excellent. Great summary. Thank you. So we have time for questions, and maybe we can just open it up also to a general discussion. Let me see if I can see any hands here. Any questions? Felix, go ahead. Felix, we don't hear you if you're speaking.
Sorry. Hi, Jacco. A nice talk. Jacco, what you could conclude? Do you have some surprises or just more or less not very high significance results that you could not make a very strong conclusions? I mean, what before the observation you expected and what you have now, how you could comment on that?
Well, first of all, we detected in all supernova remnants that I showed here, we detected polarization. So we have a significant result, sometimes with some effort, like in case A, individual pixels maybe not, but as a whole, we know it's radially oriented magnetic field. So we in statistical, it's significant. Case A and Tycho and so on were maybe not so surprising because we find the same geometry of the magnetic field as in the radio. But we now know that it is very close to the shock front. So I think that's new. So we know that whatever is stretching the magnetic field, it already has to operate within 10 to the 17 centimeter of the shock front. And then we were getting used to it, and then we got ourselves surprised because now it turns out that RCA 1713 and Villa Junior, we have a tangential magnetic field. And for RCA 1713 was the first measurement even there. So I naively always thought the X-ray singleton has to do with very efficient cosmic ray acceleration, and maybe the efficient cosmic ray acceleration automatically means a radial magnetic field and a high level of turbulence. And RCA 1713 is a little bit surprising in that sense, I would say.
One question just about the predictions. So the X-rays are quite different than radio in the sense that these are particles produced. You need much higher energy than 100 TeV for electrons to produce X-rays. So in that sense, we should have an amplification of the magnetic field. So that means that you expect more or less similar amount both from upstream and downstream. So in downstream, there's compression, but in upstream, you have also strong amplification of magnetic field. So in that case, both could contribute, but how the theories are solid or could provide detailed predictions for magnetic field in upstream. So in that sense, how safe is to compare with predictions?
Well, I don't think we have a lot of predictions what happens downstream. First of all, I think it's not true that there should be X-ray singleton coming from the upstream, because you always have the compression of the magnetic field, right? And then if you have, say, a factor of 2 compression of the magnetic field, that is already a factor 4 in singleton emission. So most of the singleton emission, or you know, the dominant fraction of the singleton emission should come from downstream. And actually, for 1006, people have tried to measure if they could see the diffusion or the diffusive particles ahead of the shock, and they couldn't really find it. So I think most of the emission is really from downstream. And then the predictions about, say, Bell instability, most people study really the upstream. And you may expect that some of the turbulence will be affected downstream, but how much that is not quite clear. So you need quite a high level of turbulence downstream of the shock as well, which is maybe also surprising, right? I hope actually the IXPE results will result in theoreticians also take a better look at what is happening downstream. You know, I see Anatoly's hand, so maybe he has some answer about what is happening downstream. Of course, in PIC simulation, you see downstream turbulence, but you need some predictions, you know, what to compare it to. And I think that's not happening. Andrei Bykov's paper was basically setting up a spectrum. It was not a self-consistent modeling of the turbulence downstream. Does it answer your question?
Okay, thanks.
Thanks.
Jacco,
Yes,
thank you very much.
yes.
Go ahead, Anatoly.
Oh, sorry, I didn't mean to interrupt. Thank you for the great talk. I really enjoyed it. I have a question. Well, first of all, a comment. You asked what simulations show about downstream. I'm not completely sure because we don't obviously simulate that far downstream, but generally speaking, Bell turbulence will decay. I think if you go far enough downstream, you will recover the ambient fields. So my guess is that, I mean, it depends on what volume you're sampling. So it's really a competition between the cooling particles giving you certain width and the unraveling of the Bell fields.
Yeah.
But my question is, how much the spherical geometry is included in understanding your predictions here? So, I'm sorry, understanding the measurements. Like when you quote this polarization fraction, was this already deconvolved, assuming a spherical shell, or how much having a spherical shell contributes to scrambling of polarization?
Yeah, so if it's not perfectly radially oriented, and the shock certainly is not perfectly spherical symmetric, right? So then the polarization degree goes down because of the method, right? But it doesn't matter whether it's radial or tangential, that will be the same effect, but you lose a little bit of your predictivity. There is now actually a paper in the making, and hopefully that will appear soon, where we had another look at it, and there we are a little bit more confident that we find individual regions at the forward shock. And it's consistent with the few things that I showed. So there is more like 15% polarized.
But even when we look just at the edge, we're still integrating over some limb brighten, you know, we're looking through a sphere. So when I read, you know, 5 to 30%, that is presumably integrated through the sphere.
That's right, but you have extreme limb brightening, although, you know, IXPE doesn't see really the limb brightening, right? It's washed out, but we know from the X-ray image that it is a very thin.
Exactly
filament.
right. So
yeah, so basically you use information that you already have, but it could be indeed that the polarization degree intrinsically is a little bit higher, and that you wash it out a little bit because of.
Yeah, so I'm curious
-5%.
how much correction to expect, because what we model is, of course, just a plain parallel shock, but what you measure is a spherical object. So there is some correction that you probably already include, but I don't know what it is.
No, we don't really include that in our corrections. The only correction that we do is account for the thermal emission, which is already a bit difficult because it's not in every pixel clear in case A, you know, what is the non-thermal contribution to the continuum. That's a difficult
Right.
thing to do. I think we tried the best, but in future this may improve. Actually, maybe it's also interesting to say what will be in the future. There will be IXPE, which has a much higher effective area, so we can repeat this with better sensitivity. The resolution will not go up. There's also talk, you know, measuring these electron clouds and measuring the this angle phi is difficult. I think in the future maybe machine learning will help there. So we could even improve with the current observations, I think, if we get the software improved. So hopefully that will, you know, give much more than those individual hotspots.
I see. If I could follow up quickly, you showed that was quite refreshing. What was happening was the polarization of a single photon, that there was some uncertainty in where the electrons go.
Yeah.
So how much of an error bar is there on these measurements because of this uncertainty, or is this already included?
This is already included. So basically, this modulation factor takes this into account. It's based on measurements and Monte Carlo simulations. So that is a correction taken into account. And so for individual phi, you don't do that, but statistically, it's relevant.
So basically, if you say 30%, what's the plus or minus on that?
Well, okay. So this is I think if you go, let me go back to this modulation curve. So basically, you detect a Q and U. Let me see if I can find the plot. So basically, you have a Q and U. You calculate it like this, and then you divide by this mu in order to go to the true polarization. Now, the summation here, you know statistically exactly what is happening, right? That's just Poisson noise. And so that, you know, if you multiply it by 1 over mu, then you also multiply your error. So we know exactly the error. So statistically, it's okay. The systematic is maybe how well do we know this modulation curve. Although that was measured on the ground and with simulation. So I think that is reasonably reliable. But I think with new methods in the future, maybe we can get this mu up. And of course, you need much less of a correction.
Does it depend on the energy of the electron as well? I mean,
yeah, because basically the electron cloud, the number of secondary electrons depends on the energy. So the more electrons you have, the better you can determine this track. So that's why you have this, right? So basically the modulation factor goes up. So the higher you are, the better it is. So you see that at 5 kV is much better. Only the effective area goes down, so you have fewer photons. But so that's why I say around 3 is sort of optimal, enough photons. And in case A, of course, you know, between 4 and 6 kV, you don't expect much line emission. So most of the emission will be singleton radiation. So yes, it improves with energy.
yeah. Okay, great. Thank you. Any other questions? Yes, please, Shen, go ahead.
Yeah, when you're talking about the sigmas, what is the fluctuation actually compared with?
You mean the confidence
The 3
level?
sigma, you mentioned some 3 sigma, 4 sigma. What is the fluctuation actually?
I'm not quite sure if I completely understand what you're saying there, but let me see. I had so basically we use this statistic, right? If you have no polarization at all, your expectation value for Q and U is 0, but of course it will be a variance. So in practice you never measure 0, but you know, some fluctuation. So this is just a chi-square distribution.
I see.
And if the chi-square that you get out is for each individual pixel or region of interest, you get 11.8. We have a 3 sigma detection.
Okay.
But then we have to take into account the fact that we have many individual pixels, of course, so you have to take the trial factor. So in practice, I would say you have to be above 4 sigma, and then per pixel you're sort of fine. Then you had a 3 sigma level. Only in rare cases we have 5 sigma, and usually by combining whole regions, in which you also, of course, reduce the trial factor greatly.
Jacco, one more question about this the regions you took data. So for Kasei, there are a lot of hotspots. I mean, just variable even in Tycho. So actually, from which region you take data? Is just from the
Yeah. Okay.
shell?
So I'm not sure. Did I have a plot of Cas-A where I took data? No. I put it in the paper actually. I forgot. But for Cas-A we took the rim, we took the hole, and so the outer ring plus this western part, that's this one, and the entire supernova remnant. So you know, the outer ring is of course a forward shock, so that we detect at a 4 sigma level.
Yes.
And the hole actually at close to 5 sigma, but the polarization degree is probably low because there, of course, is you know, not from everywhere you get singleton emission. So actually, the values here are uncorrected for thermal emission. The final version that we quoted is always corrected for thermal emission. And then for Tycho, I must say, in hindsight, I don't like the fact that some of these regions are overlapping, for instance, B and F. So F was really done because we found this region here in the smoothest technique. So it's clear that the polarization is very high, or you know, not very high, but it's highest here. So here we have a solid detection. So we took that to analyze further. So we took this extraction region, we took this focusing on the stripes, and we took a few other regions, plus the outer ring. And here you see all. So we use several extraction regions.
But for Kasei, it's just you don't distinguish between forward and reverse shocks, right? It's just general.
The reverse shock is difficult, but the reverse shock is covered by this western part. Now I only show the 3 highlights where we have more than 4 sigma. So outer plus west is more than the outer ring. So that sort of suggests that we improved the statistics there. The west by itself, which would be where the reverse shock is very strong, we didn't get a 3 sigma detection. You know, there's probably some polarization signal, but it's not high enough to really call it. Now, if you look actually, so I skipped this slide. Let me see. So here we have 2 hotspots. So this is one particular binning, but if you bin a little bit more coarse, you see that you get emission from here. This is probably reverse shock related. And if you look at something that I did later with the smoothing technique in one of the later plots, here it is. So here you see actually that it looks like this whole region is non-thermal, is highly polarized. So you see both the forward shock and the reverse shock. So this could be a spot where the reverse shock is important, and this as well. The smoothing technique is a little bit experimental, right? I like it, but not everyone agrees to it. That's why it was not put in the paper. But there's a new analysis by another group, Alessandra Mercury, who found actually along the rim a couple of other ones. But I would say that here we have a good case for the reverse shock, and here as well.
Mm-hmm.
But it's not maybe not a solid detection that everyone agrees to.
So, I mean, what is the plan then? I mean, are you going to look at these sources with deeper exposure to, I mean, more data?
Yeah, but then we need to get more time. So we have one other pointing on 1006, which is the southwestern part. That's part of the guest observer time. That's a paper that is in the making and will be soon published, hopefully. We have yet another one, RCW86, that is in the making. And I think that's basically it. So, you know, we would like to get more time. One thing that is not observed yet is a Kepler supernova remnant. So we will push for more observations. And as I said, then in the future, maybe if we improve our core technique to measure this phi, we say with machine learning, maybe we can improve even with the existing data.
Mm-hmm. Mm-hmm.
And then for the longer term future, say,
but what to expect with SIG?
I'm sorry?
And what will give you a couple of years? So square root of t, you expect improvement of like traditional square root of t, or
I
just
think
this
we
more
can get,
sophisticated?
you know, maybe. Yeah, that's a good. I think we can gain maybe even factors of 2 if we really improve on phi.
Mm-hmm.
If we really improve on getting the accuracy of getting this photo electron, right? So as the image showed, it's a very difficult measurement, and there's some geometric algorithm that takes care of this. But certainly, you accumulate errors that way. So if you can do much better on that, that will improve. I think actually IXPE has an effective area that's 4 times bigger. So there we may gain a factor of 2 or so in accuracy, which is really very good, right? Because many of these hotspots we didn't really try to call because it's on the 3 sigma level. So a small improvement really may lift it over the 3 sigma level.
Okay, any other questions? I guess not. Thank you. That was really an excellent summary and just learned a lot. It was very nice that you spent so much time on the, in each point. Felix, if there are no other questions, should we close the session for today?
Well, maybe just, if you don't mind, it will be interesting to ask the people who did some calculations or working on the theory, like Andrei Bykov is here, I hope still.
Oh, okay.
How he'd comment on these results, just for curiosity, I mean.
That's a good question, actually. I was going to ask also, because you showed some models and predictions. It would be good to hear some theorists.
Yes, we model type case, which is relevant also to CASA and 1006. And model is what we have indeed fast shock with Mach number more than 30. And in this case, as it was shown by Caprioli and other simulations, Bell instability is dominating in the upstream. And so we use our nonlinear Monte Carlo code, which we did with Don Ellison years ago, to calculate the current of escaping cosmic rays. Cosmic rays are accelerated in Tycho up to 100 TeV, but the highest energy protons do escape accelerator. They cannot be confined there. And then they escape accelerator, they create current, electric current, which is the basic point of Bell instability. So then we calculate the amount of this current. We put this number to MHD code. We use MHD code because it allows to study nonlinear phase of Bell instability. And indeed, if you have developed Bell instability, it creates, apart from strong magnetic field fluctuation, which Jacco discussed, also strong density fluctuation of short scale. Strong density instability of large scale is easy to get from ISM or circumstellar medium, but short scale, strong density fluctuation, like scales of 10 to the 17, are basically absent in the upstream. But Bell instability at nonlinear stage produce them, and then interaction of with density fluctuation with shock create corrugation of the shock. That corrugation, as we see from simulation, create anisotropic vortex motions of plasma downstream, and that vortex produced by standard short scale dynamo anisotropic magnetic field turbulence. So we have indeed a very turbulent field, as Jacco mentioned, which is needed for particle acceleration, but turbulence in the downstream from this MHD simulation is very anisotropic at short scales after shock, and that produce apparent radial. So it's indeed very turbulent, but with preferential direction of the field, radial direction, and that we believe what it can indeed explain the data of the great data by IXPE, which Jacco discussed. And indeed, in our case, if we go to low density stuff, like Villa Junior or so, indeed, there are some problems with creation of that fluctuation, and that may explain probably tangential field in this. So that's basically what I can say. It's a model, it's published in Physical Review D last year.
Yeah. More general question, Andrei. May I just, I'm sorry, to ask, I formulated my question to Jacco. I mean, not very well. So of course, its main emission comes, main portion comes from downstream. But my question was, I want to say, actually, why people are modeling in upstream? Why upstream modeling, I mean, amplification should have impact on the results? So you said they are just doing all these simulations, but do we expect some impact of what is happening in upstream since the radiation comes from downstream? I just really formulated the wrong way. I just want to ask why people are putting so much emphasis on modeling upstream.
Felix, in the model that I explained, everything is going in the downstream. So only initial Bell instability, of course, in the upstream. So cosmic ray instabilities are in upstream, but creation of anisotropic.
That should not work.
And actually, as Anatoly mentioned, indeed, in our case, this turbulence is degraded after some distance and goes to some level, background level. So it's indeed the case here because we have no extra source. So we did not imply any cosmic ray instability in downstream. They can be, but that is a matter of not MHD case. It's a matter of particle itself.
But I think this is an important point, right? I mean, we have these simulations. Theoreticians say it should the turbulence should go downstream. I think what we show is it doesn't go down too much. So it gives you a sort of a length scale over which apparently it hasn't gone down. I don't think we have a very good idea what that length scale should be. but there's some now observational data. It's maybe telling that in RxA 7013 we see the highest polarization degree very close to the shock front, and not so much further downstream, which is also a little bit weird, right? Because if the turbulence goes down, you expect a higher polarization degree. It's not something that we currently see. And the other thing to think about, I don't think we have the answer.
Jacco, sorry to interrupt you, but indeed, you cannot see regions where turbulence goes down because it's low magnetic field already.
That's right. So also maybe the magnetic field itself goes down, but to some extent we can do maybe a little bit better, right? Because if the magnetic field goes too much down, we don't expect to see any extra singleton emission at all, right? Although we have to take into account projection effects.
Sure.
Yeah. And the other thing is, you know, if you turn down the Bell instability, say in RxA 7013 and Villa Junior, you shouldn't do it too much, because you still need the turbulence and the amplification to get your X-ray singleton radiation. So there's a fine balance that we have to strike there, I think, or nature apparently.
Jacco, apart from Bell instability, there are resonant and other things.
That's right. Yeah.
Which actually, as I said, from, for example, hybrid or peak simulation should dominate as the modest Mach numbers. So that's qualitatively it's consistent.
Okay. Yeah. Oh, that's interesting. Yeah.
All right, it is 1:30, so I think we should stop here because a lot of people have to leave, including Jacco. Thanks again for a really excellent seminar, and I just encourage everyone to join again in 2 weeks. We have Yuri Putanen, and he will also talk about IXPE studies and focusing on accreting black hole binaries. So thank you all for joining, and great talk, Jacco. Please send me your PDF, okay? Because we will.
Yes, I will.
On our...
Yeah.
All right, bye-bye. See you in 2
Okay,
weeks.
thank you.
Okay,
Bye-bye.